This is it. Welcome back. We're here. This is the last lecture of this 4-lecture series module of synchronous digital systems. This is it. We're the climax. Come on, band. Climax, crescendo to the final piece. Dun, 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 dun. Oh, the joy. Where we're looking at, we're trying to build a subtractor, the final design of subtractor, and it is extremely clever. And you'll see why this is clever. I don't want to have to build, just to step back, don't look at the screen, don't look over here, look at me. I don't want to have to build 32 bits of an adder, which does its thing, and 32 bits of a subtractor, and then choose in a mux between them. I'd like to be able to reuse that machinery. So can I possibly reuse the machinery for my cascaded adder for my subtractor? Here's the big idea, I love this idea. A minus B is the same as A plus negative B. Like, duh, yeah, I get that. But how does that embody itself in the circuit? I love this part. See this little graph over here, this little truth table? It's an XOR. Do you remember that slide I showed you before? I actually probably showed you this truth table. When X is 0, Y, the output is just Y. It's just Y. When X is 1, it switches. It's not Y. We call this a conditional inverter. So, A plus negative B. Sometimes I want to add A plus B. Sometimes I want to add A plus negative B. How do you negate, this is so fun, how do you negate a 2's complement number? You invert the bits and add 1. Subtract goes high. When this line goes high, I'm so pleased because I just love this slide. This is the crescendo of all the fun. And it really is very clever. When this subtract line goes high, I feed that into here that is shared from each line of B. I need 32 of these guys, or end of these guys. Each of those bits, let's watch this, each of those bits independently is going to be flipped. Remember, a 2's complement number, you flip the bits. This does that. Each one of these gets their bits flipped. When this goes high, each of them, if it's a 1, becomes a 0. The output is 0. If the input for B of n minus 1 is a 0, the output is a 1. It flips the bits. And add 1. I had this port sitting over here. I'm just too pleased with myself. That was like, is it wiggling? Do I let it go? Do I not plug anything into it? I said, well, let's put a 0 there. And it's true, 2 unsigned numbers, I better put a 0 there. But I want to be able to flip the bits and add 1. This is your add 1. Flip the bits and add 1. And you are now calculating A minus B. A plus negative B, which is the same as A minus B. So I can reuse my entire subtractor, all the adders, the 1-bit adders from my adder, to be able to do a subtractor by just flipping B's bits and adding 1, and now I've flipped B, now it's negative B. Now the bit representation is negative B. A plus negative B, A minus B. This is my what? This is my what? This is my signed overflow, okay? My signed overflow. By itself is my unsigned overflow, okay? So remember, XOR of both of these channels, and C of n minus 1 and n, we just talked about that, is my signed overflow. Just take this line straight, that's my unsigned overflow. Unsigned, I should write this here. Unsigned overflow. Okay? You can't read my handwriting, but I can't either. When you get to be a PhD, you can write, scribble, and people can't tell what's happening. That's it! I'm so excited! So, in summary, use muxes to be able to do a flag person on the line. I got 2 signals to come in, but I only have 1 output. I use a mux to be able to drive who gets to drive the output, who gets to drive across the bridge, okay? If I have S input bits, I select from among 2 to the S inputs. We saw 1 bit chooses among 2. 2 bits chooses among 4. So S bits chooses among S 2 to the S inputs. Each input themselves independently can be n bits wide. That could be 2, that could be 4 1-bit lanes driving a 1-bit output, or 4 n-bit lanes, n-bit input lanes, all driving 1 n-bit bridge. Okay, that's pretty cool. I can implement those muxes hierarchically. We saw that thinking the NCAA tournament. My ALU can be implemented using a mux. I do all these calculations, and then I just at the end use the muxes to figure out who drives the output line. And I can use, to build an n-bit adder subtractor, I can use n 1-bit adders, cascade them together, and use an XOR to determine the signed overflow. That's pretty cool. This is really good stuff. So we literally, if I go back 4 lectures ago, and several hours in one long recording day for me, I started by talking about a transistor and what having voltage turning on and a gate to be able to have what a bit means. How do you even go from current flowing or not flowing to a bit? How to wire them to get some basic low-level structure, how to make a NAND gate, how to build up, how to look at signals and waveforms, how to then ignore those signals waveforms and think about, and so some timing in there, how to think about how would you build combinational logic circuits, what's some Boolean algebra behind that, how do you massage it, how do you get your hands all stuck with lotion to massage a Boolean expression down to its simplest form, maybe fewest gates. And then how to take some of those basic gates to build them to higher level blocks we're going to use in our data path to be able to build together a working machine to process RISC-V machine code and actually get this working. That's the next 3 lectures. I cannot wait to see you there. Awesome, folks. Thank you so much for coming to these STS lectures. We'll see you the next time.